welcome back. So, so far, what we've done in this topic is talk about mathematical induction. And mathematical induction is really just one method in order to make a proof. So it's basically an extension of the proof methods that we already know. But right now, we're going to do a 90-degree turn and we're going to talk about this thing called a relation. We're going to come back and do a little bit more on mathematical induction a little bit later in this section. But for now, I just want to introduce a new concept. This is a definition, so take it as a definition, but we will go on and talk a little bit more about relations um, uh, in the next topic, in the next few topics. Um, in this section, we're also going to introduce this thing called a function, and once again, functions. We'll talk a lot more about that in the next topic as well. But for now, let's just give a definition to what these things are. So a relation is related to Cartesian products. So if you remember what Cartesian products from before, they are a basically ordered tuples, right? So when we had something like A cross B cross C, then we had a tuple that had three elements, right? The first element comes from A, second element comes from B, and the third element comes from C, and that's what a cross product represents. But what a relation is, the official definition of a relation is any subset of A cross B given two sets. Okay, so I'll give you a very quick example. Now, I'm not really going to show you what the application is until we get to the topic on relations later. But let me just give a very quick example. Let's say A is the set 1, 2, and B is the set 3, 4, 5. Okay, then we can say that A cross B is all of the tuples that involve two elements. The first one comes from A, the second one comes from B. So we have 1, 3. We also have 1, 4, 1, 5. We also have 2, 3, 2, 4, 2, 5. Right. So essentially, there are six items in A cross B. And we said there's an equation that goes with that. So so if we ever wanted to find the size of A cross B, right? So A cross B, we said it's size of A times the size of B, right? So this is how we find the size of the cross product. Now, that's not the important thing, although you should probably remember this for a later discussion. But let's take an example of a relation. Now, a relation just means there's some relationship between set A and set B, and we want to define that relationship. So we can say R1, for example, is a relation. So I take a subset of these things. Let's say I take 1, 3 and 1, 4. Okay, so what we're saying here is that there's a relationship between set A and set B, and that is that one is related to 3, and one is already, and also one is related to 4. So that's it. That's the relationship between set A and set B. Now, this is just an example. Okay, so just I want you to see that this is just one example of a relation from set A to set B. So here's another example. I can say R2. We could have 2, 4, 2, 5, 1, 3, 1, 5, and that's it. All right, so this is another example of a relation. So as the definition down there suggests, any subset of A cross B is called a relation. Okay, so we can call any subset of A cross B an example of a relation. Even if we had a relation that is empty, this is still a subset of A cross B. And in this case, what we're saying is that there's no relationship between set A and set B, right? So the elements in A have no relationship to to the elements in B. Now, what would be a good example of, or what would be a good practical example of A cross B, or for that matter, a relation from set A to set B? So let's say, for example, we have a set of students. Okay, so we have a set of students in set A, and set B, we have a set of courses. Okay, so what would we get if we take A cross B in that case? Well, we would get all the students crossed with all the courses, right? So we would have, student A crossed with course one, student A crossed with course two, and so on, right? So you can imagine that you have all the students and all the courses crossed together. So this represents a possible enrollment for a particular semester for maybe a university. right? But what is the actual enrollment? The actual enrollment is who actually takes what course, right? So which student is actually taking which course. So it's not really a crossing between all of the students and all of the courses. Instead, it is a subset of that. So a subset of that would be a relationship between students and courses that represents the actual enrollment. Okay, so I hope you can see that that is one example that we can have of a relation, right? So the relation of students taking courses, right? So we're going to see many examples of this going forward when we get into the section on relations. But for now, just take it as an example. The last thing I want to say is if I give you generally, so given sets A and B, okay, generally, if I give you sets A and B, how many relations are there from A to B? Okay, so the total number of relations from A to B is how much? Well, you can see in this example, we've already listed 3 relations. How many more can we list? Well, the answer is this is identical to the subset equation because as the name suggests, the relation is any subset of A cross B. So the question is, given sets A and B, how many subsets are there? And the answer is that since we have a cross B and the size of A cross B, each one of those objects have 2 choices. They can go into the subset or they can be left out of the subset. So the answer here is 2 to the size of A cross B. Okay, 2 to the size of A cross B. So in our previous example, the answer is 2 to the power of 6, which if you want to write it out like this, it's the size of A times the size of B. Okay, so 2 to the power of the size of A times the size of B. Okay, now again, I'll just leave this as a definition. We're going to do a lot more work with this going forward, but I just want you to have an idea of what a relation is, what the definition of a relation is. But how do we define a relation typically? So, so relations can sometimes be expressed in set builder notation. Okay, so set builder notation, if you remember, is the way to describe a set using some mathematical formula so that you can grab, or so you can calculate all of the individual elements. So for example, let's say I have a relation R. Okay, this is a relation R, and it is a subset of Z plus cross Z plus. Okay, so anytime you see a notation that looks like this, then you basically can say, yeah, we're dealing with a relation. So here you can imagine that we have tuples in which the first element is a positive integer, the second element is also a positive integer. So we have a bunch of those tuples. So for example, I can give you the definition of this relation as xy such that y is equal to 7x. Okay, so if this is the relationship between the x and the y, then I can now list a bunch of tuples that belong in this relation. So for example, I can say that what else? 117 is in this relation, 214 is in this relation, 321 is in this relation, and so on, right? So I can list a bunch of elements that are in this relation. Okay, so this is just one way that we can define a relation using set builder notation. And again, we're going to come back and do a lot more work with this a little bit later on. Now, there is a theorem here that I very quickly just want to prove, and for nothing else, I want to show you this element proof once again. We did do an example of an element proof earlier in the course, but I just want to show you one more here. So we have part A. So I'm going to prove part A. The other parts are actually very similar to part A. So I'm going to do part A, and I'm going to leave the rest of them for you to try out. And again, if you have any trouble, let me know. So I'm going to use an element proof to prove this. All right, so the element proof goes like this. Let's imagine that xy is in the set A cross B intersects C. Now, if you take a look at the right-hand side, or sorry, the left-hand side of this expression, we have A cross B intersects C is equal to, so has the same elements as A cross B intersect with A cross C. Okay, so the element proof goes like this. For every single element, I want to make an argument that that where these elements are. So first, let's start with if if xy, if the element xy is in A cross B intersects C, then surely x must be in A, right? X must be in A, and y must be in B intersects C, right? So because we have this tuple xy, we know that x comes from the first set and y comes from the second set. So I hope everyone can see that. Now, to expand this a little bit, what does y in B intersect B, C mean? It means that y is found in B and y is found in C. So I'm going to expand this and say x is in A and y is in B and y is in C. Okay, so this is what we have so far. Now, from here, we can quite simply go to the other side and say that x, y is found in A cross B. So if x is in A and y is in B, then xy must be in A cross B. What else? And xy must be in A cross C, right? Because x is in A and y is in C. So therefore xy must be in A cross C. So what can we gather from that? We can gather that xy must be in A cross B intersect A cross C. And that's it. So there is our proof. Well, actually, I shouldn't say that's it, because the argument that I just made here is a one-directional argument. But if you take a look at every step that we took, every step could actually go backwards. So for example, I can say xy in A cross B intersect A cross C can go back and say xy is in A cross B and xy is in A cross C. Yes, I can go back up to the previous step. This one, I can go back up to the previous set. This one, this one, I can go back to the previous step. And this one, I can go back to the previous step. So it turns out that the argument that I just made is a two-directional argument. So this is what completes our proof. All right. So again, I will leave part B, C, and D for you to try. Use the same argument, use an element argument in the same way and see if you can prove all of the other theorems as well. Now, quick hint, if you're looking at part B, your first step is to say that xy is in A cross B union C, right? So if you're doing part B, right, this is going to be your first step. Now, just a hint, when we break this apart, we're going to get x is in A and y is in B or y is in C. Okay, so you're going to get something like, well, let me write it out. X is in A and y is in B or y is in C. Now, what does this remind you of? This is a distributive law. Okay, so there's the hint. Use the distributive law in order to prove this theorem. Okay, so try that. If you have any trouble, please come see me or please send me an email. Okay, now, so far, I've given you a quick introduction. I've given you a quick definition of relations. Again, as I said, we're going to come back to this, the whole idea of relations a little bit later in the course, but now I want to give you another definition, which is based on top of that. So a function is a mapping. Okay, so you probably all heard of functions before, but let me just be clear on how we're going to define a function in this course. So let A and B be sets. A function or a mapping f from A to B is an assignment of one element of B to each element of A. Okay, so again, a mapping from set A to set B is an assignment of one element of B to an element of A. So another way to say this is that each element of B is unique to A. It's unique to A. So whenever we say there's a function or a mapping between set A and set B, we typically use a notation that looks something like this. And you've probably seen this notation from math, right? F of A is equal to B. Now, assuming that small a is from the set A and small b is from the set B, we call A the input and B the output. Okay, so A is the input, B is the output. So when we say f of A is equal to B, we say, we call this a bunch of things. We can call this A maps to B. Okay, so we can say that A maps to B. We can say that the input of A gives me the output of B. We can also say that B is unique to A. Now, there's that word again. Remember, in one of the past videos, we defined very extensively what the definition of unique is. And right now, I want to use that definition once again to give you a full definition of a function. Okay, so here's the full definition of what a function is. So since B is unique to A, another way of saying that is you cannot have one input that gives you multiple outputs. Okay, so you cannot have an A that gives you multiple Bs. That would not classify as a function. So let's see how we can say B is unique to A. So again, I just want to remind you that uniqueness, there's two parts to it. Number one, at least one. Okay, at least one is part of uniqueness, but also at most one. Okay, so for every A, there's at least one B, and for all A, there must be at most one B. That is the official definition of a function. So let's try to write that out. So the first part is at least one. Okay, so this is the at least one. So again, for every A, for every input, there's at least one output. So how do we write that? So for all A, there's at least one B, so that f of A is equal to B. Now, since I wasn't clear before, I should mention that A is found in A and B is found in B. Okay, so A represents an element in set A and B represents an element in set B. Okay, so what I just wrote down for number one here is the statement at least one, is the statement that every input has at least one output. So for all A, there exists a B, so that f of A is equal to B. Okay. The next part is at most one. So for every input, there's at most one output. So how do we write that? Well, for every input, say for every A, let's imagine there is a B1 and a B2. So if f of A is equal to B1 and f of A is equal to B2, what can we say about B1 and B2? They must be equal. Now, I hope this looks familiar, right? Because this is the same argument that we made about the uniqueness, that a uniqueness example that we did before, right? So here we go again. We'll read this one more time. For every A, for every A, B1 and B2, if f of A is equal to B1 and f of A is equal to B2. So if you have an input that goes to two different outputs, that cannot happen. Okay, there's a guarantee that B1 is equal to B2. Okay. Now, I know a lot of you have taken math and you've actually had a rule in math that says whenever I have a function, right, whenever I graph it on the graph, and I have this vertical line test where this line touches the graph two times, this will not be a function. So this is what I'm talking about here in part two. So if A has a B1 and B2, right, this cannot happen because in this case, this would be a counterexample to the statement that we just made. You see here, we have A goes to B1, A goes to B2, but B1 and B2 are not equal, right? So there is a counterexample right here. So in this case, this is not a function. So this is, well, let's say this is our counter example for number two. But what about a counterexample for number one? So a counterexample for number one is if I ever along the plane, like let's say we have a graph and then suddenly we don't have an input. Okay, so let's say we have this A here, right, that doesn't have an output, right, doesn't have a B. So right away we can say this is not a function, right? So this is not a function because in this case, the function at A does not exist. Okay, so here's another counterexample for our example number one, or sorry, for our definition number one. So definition number one says for all A, so for all inputs, there's at least one B, right? But here you can see that there's an A that has no B. Okay, so there is another counterexample here. I think I'll give you a better example, one that you probably have seen in math before. So what if A was like an asymptote? So what if you had a function that looked like this and then like this? Okay, so you can imagine that nothing touches A. Okay, now under our definition, this is not a function. Okay, so if there's a counterexample to number one or to number two, right away you say this is not a function. Now I know that you're looking at this and saying, wait a minute, this counterexample for number one, it does look like one of the functions that I've seen in math, and it is. But the definitions that we're going to give in this course is not the same as the definition of a function in math. Okay, so we actually require a little bit more constraint. We say that every B or every A, every input has a unique B. Okay, B is unique to A. Okay, so let me say this one more time. So every input has to have at least one output. Every input has to have at most one output. So therefore, every input has one and only one output. Okay. All right. So that's our definition of the of a function. So let's give an example here. Okay, so we want to find out whether or not what I'm proposing here is under our definition a function. So let's say I have the set A, which is the set of people. Okay, so A is the set of people. Set B is the set male and female. Okay, it's a gender. Okay, so now what I want to do is define a mapping. Okay, so this is a define a mapping, and before we get into it too deeply, I should note that every function, every mapping that I define is also a relation. Okay, it's also a relation between set A and set B. So right now, what I'm defining is a subset of A cross B. So here's the definition. I have AB, so I have the tuple AB such that A has gender B. Okay, now notice that F is a subset of A cross B here. Okay, so A cross B, is the set of people crossed with this male and female. So the subset of that I'm going to define as a relation between set A and set B that is true when A has gender B. Okay, so everybody has their gender associated with it. Okay, now what we want to define right now, or what we want to ask ourselves right now is this a function? Okay, so is this a function from set A to set B? So let's go back to our definition. Our definition says both number one and number two have to be true. So number one says every A has at least one B. Okay, so in this case, is it true that every person has at least one gender? Yes, I think that's true. So I'm going to say that number one passes. Okay, so does number one pass? Yes, it does pass. That is a true statement. Every person has at least one gender. What about number two? Number two says every person has at most one gender. Okay, so is that true? Every person has at most one gender. Yes, that is also true. Okay, so these two things put together, the logic is that everyone has one and only one gender. Yes, that's a true statement. So what we can gather from this is that it does pass test one, it does pass test number two, so therefore it must be a function. So this is a valid function. So in this case, how we would write it is we say F is a mapping from set A to set B. And this is just a notation that we would use. So F is a mapping from set A to set B. So not only is it a relation, but it's also a function under the definition that we've given. Okay, so every input gives us one and only one output. That's the definition of a mapping. Okay, so let's see if we can do another example here just to make sure that we can wrap our heads around this definition. So let's say that I give you the following. Okay, so we'll call this 715. So I'm going to give you the set A, which is 1, 2, 3. I'm going to give you the set B, which is 4, 5, 6. All right, so now I'm going to define a relationship. So F is a subset of A cross B. Okay, and the subset of A cross B looks like this. So F is going to be equal to 1, 4 and 2, 2, 5. All right, so my question here is this a function? Okay, so is this a function? So, well, we can go back and we can analyze each one of those definitions that we had for being a function. So number one was every input has at least one output. Okay, every input has at least one output. So what are the inputs here? Well, it's 1, 2, and 3. It's the set of A. So is it true that every single input has at least one output? And the answer is no, because 3 doesn't have an output. So 3 doesn't go anywhere, right? So from that fact, we can say that if f was given to me like this, then no, this is not a function. Okay. However, what if I add this? What if I add 3, 4? Okay. So now, is it a function? So I go back to the first definition. Every input has at least one output. Is that true? Yes, that's definitely true. So every output has at least one output. All right, what's the second part of the definition? Every input has at most one output. Is that true? Well, I think so, although some of you might be looking at this and saying, wait a minute, the number 4 is actually used twice. Is that okay? So does that violate the fact that we have at most one outputs for every input? And the answer is no, it doesn't. Because if you take a look at our previous example, is it okay that we have many males? We have 2 people who are males? Is that okay? And the answer is yes, because the outputs can be used multiple times. Okay. In fact, I think a good way to determine whether or not it's a function is we can write out something like this. So here we have set A, and here we have set B. And one good way in order to analyze whether this is a function is simply to draw arrows from inputs to outputs. So here I have 1 goes to 4, right? So input 1 goes to output 4. Input 2 goes to output 5, and then input 3 goes to output 4. So that is our that is our function. That's what it looks like. And what you see is that every input has one and only one output associated with it. Or another way to say that is in this graph, there's only one arrow pointing away from the inputs. Okay, there's only one arrow pointing away from the inputs. So that tells you that this is a function. Okay, so if we ever see that there's an input that has no output associated with it, right away we can say this is not a function. So if we see a graph that looks like this, then no, this is not a function. Also, if we see a graph that looks like this, if we see 2 goes to 5 and 2 goes to 6, that is going to violate the example, or sorry, our definition part 2, because now the input A has 2 outputs. Okay, so just please keep that in mind. They are kind of like counter examples that we should look for to see whether or not we actually have a function. All right, so now what we have is 1, 2, and 3 all have one arrow pointing away from it. So therefore, we can say that this is in fact a function that maps from A to B. Now, whenever we have a function that maps from A to B, there are some definitions that go with it. So for example, I can say that for this function that maps A from A to B, there is a domain. Now, what domain means is, in short, it means the set of inputs. Okay, so the set of inputs is pretty obvious usually. It's just equal to A. All right, so in this case, it's just 1, 2, 3. Okay, this is the domain. This is the set of inputs that we have. All right, the second definition is called a codomain. Now, a codomain, in short, is just B. Okay, so it's the set of possible elements that can take part in this mapping. Okay, it's a set of possible elements that can take part in this mapping. So it's 4, 5, and 6. Okay, thirdly, we have what's called a range of this function, and it's denoted as f of a. Okay, so that's the denotation. So the range is another set. It's the set of values that are actually used from the output. So from the domain, from the codomain, what is the subset of values that are actually used in this function? And the answer in this case is 4 and 5. Okay, so 4 is used, 5 is used, but 6 is never used. So 6 is not part of the range. So what you should find is that the range is always going to be a subset of the codomain. It's always going to be a subset. Whether we use all the elements or we only use one of the elements, the range will always be a subset of the codomain. Okay, so let's do a very quick example here. And we're going to start with let's start with a relation. Okay, so I'm going to have a relation F, which is a subset of Z plus cross Z plus. Okay, so my question is the following a function? And if so, what is the range? What is the domain? What is the range of this function? So I have this F that is xy such that y is equal to x squared. All right, so this is the relationship between element x and element y. So you can imagine that, we have a bunch of pairs. And by the way, the x and y's are both z plus, right? They're both in the set z plus, so positive integers. All right, so here, what we want to find out is what is the domain? So the domain is z plus. It's A. It's the set A. Okay. And then what is the range of this function? Oh, by the way, we should probably convince ourselves that it is a function first. So the first thing we should ask ourselves, is it true that every input, every x, gives us one and only one y, right? One and only one y. So is it true that x gives us at least one y? Every x gives us at least one y. Yes, it does. Is it true that every x gives us at most one y? So is there an x that would give us two y's? And the answer is no. There's no x that gives me two y's, right? So for example, it goes to 1, right? 2 goes to 4, and 3 goes to 9, and so on, right? So the range, so this is actually a function. We can call this a function from z plus to z plus. And so the domain is z plus. What is the range here? Now, you might argue that the range is also z plus, but it's actually not true, because there are certain elements that are in the codomain in Z plus that are never used. For example, I never use the number 3. I never use the number 7, right? So the range are just the squared numbers, 1, 4, 9, 16, 20, 25, and so on. Right, so this is the range of this function. All right, now we have to be very clear here. We have to be very careful about how we define our domains and our codomains, because sometimes if we're not careful, we can actually mess up the function. So what do I mean by that? So let's say, for example, that I have the function that we have z. So this is the same function, but this function goes from z to z plus. Okay, so let's say I define the same relationship, xy, such that y is equal to x squared, but this time I make my domain to be z. Okay, so what is our range this time? Well, you might argue that the range would now include 0, because 0 would be a proper input. It would be actually one of the inputs I need to consider for this function. However, it's not in the codomain. So what can we say about this function? And the answer is we can't call it a function, right? Because remember what a function is. Every input has at least one output, right? Every input has at least one output, and that violates it, right? So in this case, if I said I have a function that maps from integers to z plus, and this is the relationship, this is not a function. Okay, just please take note of that. I'm just going to erase this so that we don't get messed up, but just understand that if we change the codomain or we change the domain, this might change the property of our function. Okay, so I hope you can get these definitions down. So right now, I'll say that for the relationship, or sorry, for the relations, and for the uh, and for the functions, keep it as a definition for now. Okay, so for now, just keep it as a definition because we're going to come back and we'll revisit functions and we'll revisit relations a little bit later in the course. And by then, I'll expect that you know these definitions. So again, go back and review this video. Just make sure you understand the concepts that I've talked about, but also just keep it as a definition for now. Okay, so when we come back, when we get into the next video, I'm going to talk about special types of functions that are very closely related to mathematical induction. Okay, so I'll see you when you come back to the next video.